What if the universe is hiding secrets so profound that they could change everything we think we know about reality? Picture this, a force so powerful, yet completely invisible, shaping the very fabric of space and time. It's not science fiction, it's the mystery of the universe's hidden forces. From the enigmatic pull of dark matter to the mind-bending possibilities of quantum entanglement, there are forces at work that defy our understanding. And today, we're diving into 30 of the most fascinating theories that attempt to unravel these cosmic puzzles. Theories that challenge our perception of reality, push the boundaries of science, and might just hold the key to the universe's greatest secrets. So, are you ready to explore the unknown? Stay with us, because by the end of this journey, you'll see the cosmos in a whole new light. Let's begin. Now, let's step into the shadowy realm of dark matter, a mysterious substance that makes up a staggering 85% of all matter in the universe. Yet here's the twist, it's completely invisible. You can't see it, touch it, or detect it with any of our current instruments. So how do we even know it's there? The answer lies in its gravitational pull. When scientists observe galaxies, they notice something strange. The stars on the outer edges are moving just as fast as those near the center. According to the laws of physics, this shouldn't happen unless there's some unseen mass holding everything together. That's where dark matter comes in. It's like an invisible scaffold, providing the extra gravity needed to keep galaxies from flying apart. But what exactly is it made of? While we don't know for sure, theories suggest it could be composed of particles that don't interact with light or ordinary matter, making them nearly impossible to detect directly. Some candidates include weakly interacting massive particles, or WIMP, and axions, hypothetical particles that could solve multiple cosmic mysteries. Despite its elusive nature, dark matter is a cornerstone of modern cosmology, shaping the universe on the grandest scales. Without it, galaxies as we know them wouldn't exist, and the cosmos would look entirely different. So, while we can't see it, its presence is undeniable, a silent, invisible force holding the universe together. And as we continue to search for answers, dark matter remains one of the greatest puzzles in science, challenging us to rethink what we know about the fabric of reality. Now, let's shift our gaze to another cosmic enigma: dark energy. While dark matter holds galaxies together, dark energy is doing something even more mind-bending. It's pushing the universe apart at an ever-increasing speed. Imagine the universe as a balloon and dark energy as the force that's inflating it faster and faster. But here's the kicker: we have no idea what dark energy actually is. What we do know is that it makes up about 68% of the universe's total energy content, dwarfing even dark matter. This discovery came as a shock to scientists in the late 1990s when they observed distant supernova and realized the universe wasn't just expanding, it was accelerating. This defied everything we thought we knew about gravity and the cosmos. If gravity pulls things together, what's causing this cosmic push? That's the mystery of dark energy. Some theories suggest it could be a property of space itself, often referred to as the cosmological constant, a concept Einstein once proposed and later dismissed. Others speculate it might be a dynamic field, like an invisible energy fluid filling the universe. Whatever it is, dark energy is reshaping our understanding of physics and the ultimate fate of the cosmos. If it continues to dominate, the universe could end in a big freeze, where galaxies drift so far apart that the cosmos becomes a cold, dark, and lonely place. But here's the thing: dark energy isn't just a distant, abstract concept. It's shaping the universe we live in right now, and it's forcing us to confront the limits of our knowledge. As we grapple with this invisible force, one thing is clear: the universe is far stranger and more mysterious than we ever imagined. And with every discovery, we're reminded just how much we have yet to learn. Now, let's venture into the strange and fascinating world of quantum entanglement. a phenomenon so bizarre that even Albert Einstein famously called it spooky action at a distance. Imagine two particles, perhaps electrons or photons, that become linked in such a way that whatever happens to one instantly affects the other, no matter how far apart they are. This connection defies our everyday understanding of space and time. If you measure the spin of one particle and find it spinning up, its entangled partner will instantly be spinning down, even if it's on the other side of the galaxy. This instantaneous link happens faster than the speed of light, which seems to break the rules of physics as we know them. But here's where it gets even more intriguing. Quantum entanglement might be a clue to hidden forces or dimensions that we can't yet detect. Some scientists speculate that entangled particles could be tapping into a deeper layer of reality, where space and time as we know them don't apply. Could this be evidence of extra dimensions or a hidden framework that connects everything in the universe? It's a tantalizing possibility. Quantum entanglement also raises questions about the nature of reality itself. Are particles truly separate, or are they part of a unified whole, connected by forces we're only beginning to understand? This phenomenon isn't just a theoretical curiosity. It's already being used in cutting-edge technologies like quantum computing and secure communication. But its implications go far beyond technology. Quantum entanglement challenges us to rethink the very fabric of the universe and consider that there might be forces at work that are far more mysterious and interconnected than we ever imagined. As we explore this quantum mystery, one thing is certain: the universe is far more interconnected and far stranger than it appears, and with every discovery, we're reminded that the hidden forces shaping our reality might be more profound than we ever dared to dream. Now, let's shift our focus to a theory that takes the idea of hidden forces to an entirely new level: string theory. Imagine if everything in the universe, every particle, every force, every bit of matter and energy, was made up of tiny, vibrating strings. These strings aren't like the ones you'd find on a guitar, but rather incredibly small, one-dimensional loops that vibrate at different frequencies. The way these strings vibrate determines the properties of the particles they create, from electrons to quarks to photons. It's a radical idea, but one that could potentially unify all the forces of nature into a single, elegant framework. What makes string theory even more fascinating is its proposal of extra dimensions. While we're used to thinking of the universe in terms of three spatial dimensions: length, width, and height, string theory suggests there could be as many as 10 or even 11 dimensions. These extra dimensions are thought to be curled up so tightly that we can't perceive them directly, but they might play a crucial role in shaping the hidden forces that govern the cosmos. For instance, gravity, which is relatively weak compared to the other fundamental forces, might appear stronger in these higher dimensions, offering an explanation for why it behaves so differently on a cosmic scale. String theory also provides a potential bridge between the two great pillars of modern physics: quantum mechanics and general relativity. While quantum mechanics excels at explaining the behavior of particles on the smallest scales, and general relativity describes the large-scale structure of the universe, the two theories have been notoriously difficult to reconcile. String theory, with its vibrating strings and extra dimensions, offers a possible solution by suggesting that both gravity and quantum forces emerge from the same underlying framework. But here's where it gets even more intriguing. If string theory is correct, it could mean that the hidden forces we've been exploring, dark matter, dark energy, and even quantum entanglement, are all manifestations of these tiny, vibrating strings interacting in higher dimensions. It's a bold and ambitious idea, one that challenges our understanding of reality and pushes the boundaries of what we thought was possible. While string theory is still largely theoretical and lacks experimental confirmation, it remains one of the most promising candidates for a theory of everything, a single framework that could explain all the forces and particles in the universe. As we continue to explore the mysteries of the cosmos, string theory reminds us that the universe might be far more complex and far more interconnected than we ever imagined. And who knows, perhaps one day we'll uncover the vibrations of these tiny strings, revealing the hidden forces that bind everything together. Now, let's take a step into a concept that stretches the boundaries of imagination, the multiverse theory. What if our universe isn't the only one out there? What if there are countless other universes, each with its own set of physical laws, constants, and even hidden forces? This idea, known as the multiverse theory, suggests that our reality might just be one tiny piece of a much larger, more complex cosmic puzzle. In this framework, hidden forces like dark matter, dark energy, or even quantum entanglement could behave entirely differently in other universes. For example, in one universe, gravity might be stronger, while in another, it could be weaker or even non-existent. The constants we take for granted in our universe, like the speed of light or the strength of electromagnetism, might vary wildly in these alternate realities. This raises fascinating questions. Could there be universes where dark energy doesn't drive expansion, but instead causes contraction? Or universes where quantum entanglement operates instantaneously across infinite distances, defying our understanding of space and time? The multiverse theory isn't just a wild idea. It emerges naturally from several areas of physics, including string theory and cosmic inflation. In string theory, the extra dimensions we discussed earlier could give rise to a vast landscape of possible universes, each with its own unique configuration of forces and particles. Similarly, cosmic inflation, the rapid expansion of the early universe, could have created bubble universes, each with its own distinct properties. But what does this mean for our reality? If the multiverse exists, it could explain why our universe seems so finely tuned for life. In a sea of infinite possibilities, it's not surprising that at least one universe would have the right conditions for stars, planets, and life to emerge. It also challenges us to rethink the nature of hidden forces. Are they universal constants, or do they vary depending on the universe? Could there be universes where these forces are so different that matter and energy behave in ways we can't even begin to imagine? While the multiverse theory is still speculative, it opens up a world of possibilities for understanding the cosmos. It reminds us that the hidden forces we're trying to unravel might not be fixed or absolute. They could be just one set of rules in an infinite cosmic game. And as we continue to explore these ideas, we might find that our universe is just one thread in a vast, interconnected tapestry of realities. So, as we ponder the mysteries of the multiverse, let's keep in mind that the forces shaping our reality might be just one variation in an endless symphony of possibilities. What other secrets could these alternate universes hold? And how might they reshape our understanding of the cosmos? The answers, as always, lie hidden in the fabric of the unknown. Now, let's shift our focus to a theory that challenges our very perception of reality, the holographic principle. Imagine for a moment that everything we see, touch, and experience in our three-dimensional world is actually a projection of information encoded on a two-dimensional surface. This mind-bending idea suggests that the universe might be like a hologram, where the depth and complexity we perceive are illusions created by data stored on a flat boundary. At its core, the holographic principle proposes that all the information needed to describe our universe could be stored on its outer edges, much like how a holographic image encodes a 3D picture on a 2D surface. This concept emerged from the study of black holes, where physicists discovered that the information about matter falling into a black hole isn't lost but is instead encoded on its event horizon, the boundary surrounding the black hole. This led to the radical idea that the entire universe might operate in a similar way, with its vast complexity emerging from a simpler, lower-dimensional framework. So, what does this mean for hidden forces? If the universe is a hologram, then forces like gravity, electromagnetism, and even dark energy might not be fundamental properties of space itself, but rather emergent phenomena arising from the interactions of information on this 2D surface. For example, gravity could be a byproduct of how information is encoded and processed, rather than a force acting within three-dimensional space. This would fundamentally change our understanding of how these forces operate and interact. The holographic principle also raises profound questions about the nature of reality. If our universe is a projection, then what is the true nature of the source information? Could hidden forces be part of the code that generates our reality, like the rules of a simulation? And if so, does this mean that the laws of physics we observe are just one possible set of rules among many? These questions push us to rethink not only the forces shaping our universe, but also the very fabric of existence itself. While the holographic principle is still a theoretical framework, it offers a fascinating lens through which to explore the mysteries of the cosmos. It suggests that the hidden forces we're trying to understand might not be forces at all. They could be emergent properties of a deeper, more fundamental layer of reality. As we continue to investigate this idea, we might uncover new ways to unify the forces of nature and gain a deeper understanding of the universe's true nature. So, as we ponder the holographic principle, let's consider the possibility that the forces shaping our reality are not what they seem. Could the universe be a grand projection with hidden forces acting as the brushstrokes on a cosmic canvas? The answers, as always, lie waiting to be discovered in the depths of the unknown. Now, let's take a step into one of the most provocative and mind-expanding theories out there, the simulation hypothesis. What if everything around us, from the stars in the sky to the ground beneath our feet, isn't real in the way we think it is? What if our universe is nothing more than an incredibly advanced simulation, created by a civilization far beyond our own? This idea, once the realm of science fiction, has gained serious traction among scientists, philosophers, and even tech leaders, raising questions that challenge the very foundation of our existence. At its heart, the simulation hypothesis suggests that our reality could be a computer-generated construct, much like a highly sophisticated video game. In this scenario, the laws of physics, the forces that govern the universe, and even our own consciousness might all be part of a meticulously designed program. Hidden forces like gravity or dark energy could simply be lines of code rules written into the simulation to make it function in a way that feels real to us. Think of it like the rules in a game. Gravity isn't a physical force in a virtual world. It's just a programmed behavior that makes objects fall. But what does this mean for our understanding of existence? If the universe is a simulation, then the forces we're trying to uncover might not be natural phenomena at all. They could be deliberate features of the program, designed to create the illusion of a functioning, dynamic universe. For example, dark energy, which drives the accelerated expansion of the cosmos, might not be a mysterious force but a parameter set by the programmers to keep the simulation running smoothly. Even quantum mechanics, with its strange and unpredictable behavior, could be a way to optimize the simulation's processing power, ensuring it doesn't overload as it calculates every particle state. This theory also opens up fascinating questions about the nature of consciousness. If we're living in a simulation, are our thoughts and emotions just algorithms running on some cosmic computer? Could free will be an illusion, with every decision we make predetermined by the code? And if so, what does that say about the purpose of our existence? Are we merely characters in a vast cosmic game, or is there something more profound at play? While the simulation hypothesis is still speculative, it offers a unique perspective on the hidden forces shaping our universe. It challenges us to consider that the rules of reality might not be fixed but could instead be flexible, programmable, and even changeable. If true, it would mean that the forces we're trying to understand are not just hidden, They're part of a grand design written by creators whose motives and methods remain a mystery. As we explore this theory, it's worth asking, if our universe is a simulation, what does that reveal about the nature of hidden forces? Could they be clues left by the programmers, hints about the underlying code of reality? And if we ever uncover the truth, would we be able to interact with or even alter the simulation itself? These questions push the boundaries of science, philosophy, and imagination, inviting us to rethink not just the forces at work in the universe, but the very nature of existence itself. Now, let's shift our focus to a concept that lies at the very foundation of quantum mechanics, the zero-point energy field. Even in the absence of matter or light, in what we might think of as complete emptiness, there's still energy. This is the zero-point energy, the lowest possible energy state that exists in the universe. It's a strange and fascinating idea. Even in a vacuum where nothing seems to be happening, there's a constant hum of energy, a kind of background noise that never goes away. So, what exactly is zero-point energy? In quantum mechanics, particles don't just sit still. They're always jittering, vibrating, or fluctuating, even at absolute zero, the coldest temperature possible. These tiny movements are a result of the uncertainty principle, which tells us that we can never know both the position and momentum of a particle with perfect accuracy. This inherent uncertainty means that particles are always in motion, and that motion generates energy that exists even in the emptiest regions of space. But here's where it gets really interesting. Some scientists believe that this zero-point energy field could be a source of hidden forces powering the universe. Imagine this energy as a vast, invisible ocean, constantly rippling with tiny waves. These ripples could influence everything from the behavior of particles to the structure of spacetime itself. In fact, some theories suggest that zero-point energy might be responsible for phenomena like the Casimir effect, where two uncharged plates placed very close together experience an attractive force due to the fluctuations in this energy field. Could zero-point energy be the key to understanding some of the universe's most mysterious forces? It's possible. For example, dark energy, the force driving the accelerated expansion of the universe, might be connected to this background energy field. If zero-point energy permeates all of space, it could be acting as a kind of cosmic fuel, pushing galaxies apart and shaping the large-scale structure of the cosmos. Some researchers even speculate that harnessing zero-point energy could one day provide an almost limitless source of power, though this remains firmly in the realm of science fiction for now. The zero-point energy field also raises profound questions about the nature of reality. If energy exists even in a vacuum, does that mean true emptiness is impossible? And if this energy is everywhere, could it be the foundation of all the forces we observe in the universe? These questions challenge us to rethink our understanding of space, time, and the very fabric of existence. As we explore this theory, it's worth considering how zero-point energy might fit into the bigger picture of hidden forces. Could it be the underlying source of phenomena we've yet to fully explain? And if so, what would that mean for our understanding of the universe? The zero-point energy field is a reminder that even in the quietest corners of space, there's always something happening, a hidden force waiting to be discovered. Now, let's dive into a phenomenon that brings the strange world of quantum mechanics into the realm of measurable forces, the Casimir effect. Picture this: two uncharged metal plates placed incredibly close together in a vacuum. At first glance, you might expect nothing to happen. After all, there's no charge, no obvious force at play. But in the quantum world, things are never quite that simple. What happens next is both fascinating and a little mind-bending. The Casimir effect occurs because of the quantum fluctuations we just discussed in the zero-point energy field. Even in a vacuum, space isn't truly empty. It's filled with these tiny, rapid fluctuations of energy, creating a kind of quantum foam. When two plates are brought very close together, the space between them restricts the types of fluctuations that can occur. Outside the plates, however, the fluctuations remain unrestricted. This imbalance creates a pressure difference, resulting in a measurable force that pushes the plates together. It's as if the universe itself is whispering, "Come closer." This effect was first predicted by Dutch physicist Hendrik Casimir in the late 1940s, and it was later confirmed through experiments. It's a striking demonstration of how quantum mechanics can produce real, tangible forces, even in seemingly empty space. But what does this mean for hidden forces in the universe? The Casimir effect suggests that the quantum vacuum isn't just a passive backdrop, it's an active participant, capable of influencing the behavior of objects on a microscopic scale. Some scientists believe that the Casimir effect could be a window into understanding other hidden forces. For example, it might help us explore the nature of dark energy or even the fabric of space-time itself. If the quantum vacuum can generate forces between plates, could it also play a role in larger cosmic phenomena? The answer isn't clear yet, but the possibilities are intriguing. Beyond its implications for fundamental physics, the Casimir effect has potential applications in technology. Imagine tiny machines or devices that operate on the nanoscale, where traditional forces like gravity or electromagnetism become less significant. Here, the Casimir effect could become a dominant force, influencing how components interact. Researchers are already exploring ways to harness this effect for advancements in nanotechnology, from ultra-sensitive sensors to new methods of controlling microscopic devices. Of course, there are challenges. The Casimir force is incredibly small and only becomes significant at extremely close distances, making it difficult to work with. But as our understanding of quantum mechanics grows, so does our ability to manipulate these subtle forces. Who knows, one day the Casimir effect might power innovations we can't even imagine yet. As we reflect on this phenomenon, it's a reminder of how much we still have to learn about the hidden forces shaping our universe. The Casimir effect shows us that even in the quietest, emptiest spaces, there's a dance of energy and forces waiting to be discovered. And as we continue to explore, we might just uncover more secrets hidden in the quantum fabric of reality. Now, let's shift our focus to one of the most groundbreaking discoveries in modern physics, the Higgs field. Imagine the universe as a vast, invisible ocean, and every particle swimming through it is influenced by this field. This isn't just any ocean. It's the Higgs field, a fundamental force that gives particles their mass. Without it, the universe as we know it wouldn't exist. The Higgs field was first proposed in the 1960s as a way to explain why particles have mass. According to the standard model of physics, particles interact with this field, and the strength of that interaction determines their mass. Think of it like wading through water. Some particles, like quarks, move slowly, as if they're trudging through deep water, giving them a lot of mass. Others, like electrons, glide more easily, resulting in less mass. And then there are particles like photons, which don't interact with the field at all. They're like swimmers who don't even feel the water, remaining massless. But the Higgs field isn't just about mass. It's also deeply connected to the hidden forces that shape our universe. For instance, the Higgs boson, the particle associated with the field, was discovered in 2012 at the Large Hadron Collider. This discovery confirmed the existence of the Higgs field and filled a crucial gap in the standard model. It also opened up new questions about how this field interacts with other forces, like dark energy or gravity, which remain poorly understood. One of the most intriguing aspects of the Higgs field is its potential role in the early universe. Scientists believe that shortly after the Big Bang, the Higgs field underwent a phase transition, similar to water turning into ice. This shift may have played a key role in shaping the fundamental forces and particles we see today. It's even possible that the Higgs field could hold clues about the nature of dark matter or the unification of all forces into a single, elegant framework. The Higgs field also challenges our understanding of symmetry in physics. In the standard model, particles and forces are governed by symmetries, but the Higgs field breaks some of these symmetries, giving particles their unique masses. This process, known as spontaneous symmetry breaking, is a cornerstone of modern physics and has far-reaching implications for how we understand the universe's hidden forces. As we continue to explore the Higgs field, we're not just uncovering the secrets of mass, we're also peering into the deeper layers of reality. From its role in the early universe to its potential connections with dark energy and beyond, the Higgs field is a reminder that even the most fundamental aspects of our world are still full of mysteries. And as we delve deeper, we might just find that this invisible ocean holds the key to unlocking some of the universe's greatest secrets. Now, let's take a step back and consider the bigger picture. What if all the forces we've been exploring, gravity, electromagnetism, the strong and weak nuclear forces, and even the hidden forces like dark energy and the Higgs field, could be explained by a single, unified theory? This is the dream of the theory of everything, a framework that seeks to tie together all the fundamental forces of nature into one elegant equation. The idea of a theory of everything isn't new. For decades, physicists have been searching for a way to reconcile the two pillars of modern physics: quantum mechanics, which governs the behavior of the very small, and general relativity, which describes the universe on the largest scales. While both theories work incredibly well in their respective domains, they don't play nicely together. Quantum mechanics thrives on probabilities and uncertainty, while general relativity is rooted in the smooth, deterministic fabric of space-time. Bridging this gap is one of the greatest challenges in science. So, how might hidden forces fit into this grand framework? One possibility is that these forces are manifestations of a deeper, underlying structure that we haven't yet uncovered. For example, string theory, which we'll explore in more detail later, suggests that all particles and forces are vibrations of tiny, one-dimensional strings. In this view, hidden forces like dark energy or the Higgs field could emerge from the interactions of these strings in higher dimensions. Another approach comes from quantum gravity theories, which attempt to describe gravity in terms of quantum mechanics. Some of these theories propose that hidden forces could arise from the quantum foam, a turbulent, ever-changing sea of spacetime at the smallest scales. Here, forces we don't yet fully understand might be constantly flickering in and out of existence, shaping the universe in ways we're only beginning to grasp. The quest for a theory of everything also raises profound questions about the nature of reality itself. Could hidden forces be clues to a deeper layer of existence, one that operates beyond our current understanding of space and time? For instance, some theories suggest that dark energy might be linked to the vacuum energy of the universe, a kind of background hum that permeates all of space. If true, this could mean that hidden forces are woven into the very fabric of reality, influencing everything from the smallest particles to the largest cosmic structures. Of course, the search for a theory of everything is far from over. While we've made incredible strides in understanding the universe, there's still so much we don't know. Hidden forces, whether they're tied to dark matter, dark energy, or something entirely new, could hold the key to unlocking this ultimate theory. And as we continue to explore, we might just find that the universe's greatest mysteries are all connected, waiting to be revealed by a single, unifying idea. As we move forward, let's turn our attention to another fascinating possibility: the existence of a fifth fundamental force, one that could reshape our understanding of the cosmos. Now, let's shift our focus to a tantalizing idea that could revolutionize our understanding of the cosmos: the possibility of a fifth fundamental force. We're all familiar with the four forces that govern the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But what if there's another force out there, one that's been hiding in plain sight, waiting to be discovered? This is the intriguing concept behind the search for a fifth force, a quest that could reshape our understanding of physics as we know it. The idea of a fifth force isn't just science fiction. In fact, scientists have been exploring this possibility for decades, driven by anomalies that the four known forces can't fully explain. For instance, some experiments have detected tiny discrepancies in the behavior of particles that don't align with the predictions of the standard model of physics. These anomalies have led researchers to wonder if there's an unseen force at play, one that operates on scales or in ways we haven't yet detected. One of the most compelling hints of a fifth force comes from studies of the universe's expansion. While dark energy is often credited with driving the accelerated expansion of the cosmos, some scientists speculate that a fifth force could also be contributing to this phenomenon. Unlike gravity, which pulls objects together, this hypothetical force might act in the opposite direction, pushing things apart on cosmic scales. If true, it could provide a new explanation for why the universe is expanding faster than expected. But how do we go about detecting something we can't see or directly measure? That's where cutting-edge experiments come in. Researchers are using highly sensitive instruments to search for subtle deviations in the behavior of particles or the motion of celestial bodies. For example, some experiments involve measuring the gravitational attraction between objects at incredibly small distances, looking for any signs of an additional force that might be influencing their interactions. Others are studying the properties of subatomic particles, searching for unusual decays or interactions that could point to the existence of a fifth force. One particularly fascinating area of research focuses on the relationship between the fifth force and dark matter. Some theories suggest that this new force could be the key to understanding dark matter's elusive nature. If dark matter particles interact with ordinary matter through a fifth force, it might explain why they've been so difficult to detect using traditional methods. This connection could open up entirely new avenues for exploring the hidden side of the universe. Of course, the search for a fifth force is still in its early stages, and there's much we don't yet know. But the implications of discovering such a force would be profound. It could not only fill in gaps in our current understanding of physics, but also reveal entirely new layers of reality, ones that operate beyond the limits of our current theories. As experiments continue to push the boundaries of what we can observe, we might be on the verge of uncovering a force that changes everything we thought we knew about the universe. With this intriguing possibility in mind, let's turn our attention to another mysterious player in the cosmic drama, neutrinos, and their potential role in shaping the universe's hidden forces. Now, let's dive into one of the most enigmatic particles in the universe, neutrinos. These nearly massless particles are so elusive that they can pass through entire planets without interacting with anything. Yet, despite their ghostly nature, neutrinos might hold the key to understanding some of the universe's most profound mysteries, including the hidden forces that shape our cosmos. Neutrinos are produced in abundance by nuclear reactions, such as those in the Sun, supernova, and even human-made reactors. They come in 3 types or flavors, and have the peculiar ability to change from one flavor to another as they travel through space. This phenomenon, known as neutrino oscillation, was a groundbreaking discovery that proved neutrinos have mass, albeit an incredibly tiny amount. But even this minuscule mass has significant implications for our understanding of the universe. One of the most intriguing aspects of neutrinos is their potential interaction with hidden forces. While they barely interact with ordinary matter, some theories suggest that neutrinos might be influenced by forces beyond the 4 we know. For instance, if a fifth force exists, neutrinos could be one of the few particles sensitive enough to detect its effects. Their ability to oscillate between flavors might even be tied to interactions with these hidden forces, offering a new window into the unseen workings of the cosmos. Neutrinos also play a crucial role in cosmic phenomena. During a supernova, for example, neutrinos are among the first particles to escape the collapsing star, carrying vital information about the explosion's inner workings. Some scientists believe that neutrinos could be linked to dark matter, another cosmic mystery. If dark matter particles interact with neutrinos through a hidden force, it might explain why dark matter has been so difficult to detect directly. This connection could bridge the gap between the visible and invisible aspects of the universe. But detecting neutrinos is no easy task because they interact so weakly with matter. Scientists have had to build massive detectors deep underground to shield them from other particles. These detectors, often filled with water or other materials, wait for the rare moment when a neutrino collides with an atom, producing a faint signal that can be measured. Despite the challenges, these experiments have already revealed groundbreaking insights, and they continue to push the boundaries of what we know about neutrinos and their role in the universe. The study of neutrinos is a testament to the power of curiosity and innovation. These ghostly particles, once thought to be insignificant, are now at the forefront of physics, offering clues about the hidden forces that might govern the cosmos. As we continue to unravel their secrets, we may find that neutrinos are not just passive observers but active participants in the grand cosmic dance. With this in mind, let's turn our attention to another cosmic mystery, the Great Attractor, a gravitational anomaly that's pulling galaxies toward it, and the hidden forces that might be at play in this enigmatic region. Now, shifting our gaze to another cosmic enigma, we encounter the Great Attractor, a mysterious gravitational anomaly that's pulling entire galaxies, including our own Milky Way, toward it. Located in the direction of the constellations Centaurus and Hydra, this invisible force has puzzled scientists for decades. What could be causing such a powerful gravitational pull, and could hidden forces be at work in this region of space? The Great Attractor lies about 250 million light-years away, and its immense gravitational influence affects the motion of galaxies across a vast region of the universe. Despite its name, we can't directly observe it because it's obscured by the dense plane of our own galaxy, the Milky Way, which blocks our view with dust and stars. This makes studying the Great Attractor a challenge, but astronomers have used indirect methods like mapping the motion of galaxies to infer its existence and strength. One leading theory suggests that the Great Attractor is not a single object but a massive concentration of matter, possibly a supercluster of galaxies. The Norma cluster, a dense grouping of galaxies, lies at the heart of this region and could be contributing to the gravitational pull. However, even this supercluster doesn't fully account for the immense force observed. Some scientists speculate that dark matter, the invisible substance that makes up most of the universe's mass, could be playing a significant role here. If dark matter is concentrated in this region, it might amplify the gravitational effects, creating the anomaly we detect. But the mystery deepens when we consider the larger cosmic structure. The Great Attractor itself seems to be moving, pulled by an even more massive structure known as the Shapley supercluster, located over 650 million light-years away. This suggests a cosmic tug-of-war with hidden forces acting on scales far beyond our current understanding. Could these forces be tied to dark energy, the mysterious force driving the universe's accelerated expansion? Or might there be other, yet undiscovered forces at play, shaping the large-scale structure of the cosmos? Some researchers have proposed that the Great Attractor could be a window into the interplay between visible matter, dark matter, and dark energy. If hidden forces are influencing the distribution and motion of matter on such vast scales, studying this region could provide crucial insights into the fundamental laws of the universe. It might even help us understand why galaxies cluster in certain patterns and how the universe evolved into its current state. As we continue to explore the Great Attractor, new technologies and observational techniques are shedding light on this cosmic mystery. Projects like the Square Kilometre Array, a next-generation radio telescope, aim to map the universe in unprecedented detail, potentially revealing the true nature of this gravitational anomaly. Each discovery brings us closer to understanding the hidden forces that shape our universe, reminding us that even the most elusive mysteries can be unraveled with time, curiosity, and innovation. With this in mind, let's turn our attention to another fascinating concept: vacuum energy, a mysterious force that permeates the fabric of space itself and its potential role in the universe's hidden forces. Now let's dive into the intriguing concept of vacuum energy, a mysterious force that exists even in the emptiest regions of space. At first glance, the idea of energy in a vacuum might seem contradictory. After all, a vacuum is supposed to be empty, right? But in the quantum world, even the void is teeming with activity. This is where vacuum energy comes into play, and it might hold the key to understanding some of the universe's most profound mysteries. Vacuum energy is rooted in the principles of quantum mechanics, which tell us that empty space is never truly empty. Instead, it's a seething sea of virtual particles that constantly pop in and out of existence. These fleeting particles create a background energy field that permeates the entire universe. While this energy is incredibly weak on small scales, its cumulative effect across the vastness of space could be immense. In fact, some scientists believe that vacuum energy might be the driving force behind the accelerated expansion of the universe, a phenomenon we attribute to dark energy. The connection between vacuum energy and dark energy is one of the most fascinating aspects of modern cosmology. Dark energy, as we've discussed earlier, is the mysterious force causing the universe to expand faster and faster. But what if dark energy is simply the manifestation of vacuum energy on a cosmic scale? This idea has gained traction among physicists, as it provides a potential explanation for why the universe's expansion is accelerating. If vacuum energy is indeed the source of dark energy, it would mean that the very fabric of space itself is pushing galaxies apart. However, there's a catch. When physicists calculate the expected value of vacuum energy based on quantum theory, the result is staggeringly large, far larger than what we observe in the universe. This discrepancy, known as the cosmological constant problem, remains one of the biggest unsolved puzzles in physics. It suggests that our understanding of vacuum energy, or perhaps quantum mechanics itself, is incomplete. Could there be hidden forces or unknown principles at work that reconcile this difference? Or might vacuum energy interact with other cosmic forces in ways we haven't yet discovered? One intriguing possibility is that vacuum energy isn't constant but varies over time or across different regions of space. This could explain why its effect seems so subtle on small scales but becomes significant on cosmic scales. Alternatively, vacuum energy might interact with other hidden forces, such as dark matter or quantum fields, in ways that modify its behavior. Exploring these ideas could lead to breakthroughs in our understanding of the universe's fundamental forces and how they shape its evolution. As we continue to probe the mysteries of vacuum energy, advanced experiments and observations are shedding new light on this enigmatic force. From particle accelerators to space telescopes, scientists are gathering data that could help us unravel the true nature of vacuum energy and its role in the cosmos. Each discovery brings us closer to answering some of the most profound questions about the universe. What drives its expansion? What lies beyond the visible, and how do the hidden forces of the cosmos shape the reality we experience? With this in mind, let's turn our attention to another captivating theory: the black hole information paradox, a puzzle that challenges our understanding of space-time and the hidden forces that govern it. Now, shifting our focus to one of the most perplexing puzzles in modern physics, we arrive at the black hole information paradox. This paradox strikes at the heart of our understanding of space-time and the fundamental laws that govern the universe. At its core, the black hole information paradox challenges the very principles of quantum mechanics and general relativity, two pillars of modern physics that seem to clash when it comes to black holes. The paradox begins with a simple question: what happens to information when it falls into a black hole? According to quantum mechanics, information cannot be destroyed. Every particle, every interaction carries information that must be preserved, even if it's scrambled or transformed. But black holes, as described by general relativity, are regions of space-time where gravity is so intense that nothing, not even light, can escape. If something falls into a black hole, it seems to vanish from the universe forever, taking its information with it. This creates a contradiction. Quantum mechanics says information must be preserved, but black holes appear to erase it. This dilemma became even more puzzling when physicist Stephen Hawking discovered that black holes aren't entirely black. They emit radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. But here's the catch: Hawking radiation appears to be random, carrying no information about what fell into the black hole. If the black hole evaporates completely, where does the information go? This is the essence of the black hole information paradox. To resolve this paradox, scientists have proposed several theories, many of which involve hidden forces or the interplay of quantum gravity. One leading idea is that information isn't lost but is somehow encoded in the Hawking radiation, though in a way we don't yet understand. Another possibility is that the information is stored on the black hole's event horizon, the boundary beyond which nothing can escape. This idea, known as the holographic principle, suggests that all the information about what falls into a black hole is preserved on a two-dimensional surface, like a cosmic hard drive. Quantum gravity, a theoretical framework that seeks to unify quantum mechanics and general relativity, might also hold the key to solving the paradox. Some theories suggest that black holes are not the ultimate destroyers of information, but rather gateways to other regions of space-time or even other universes. In this view, the information isn't lost, it's just transported somewhere else, hidden from our current understanding. The implications of resolving the black hole information paradox are profound. It could revolutionize our understanding of space-time, revealing new layers of reality governed by hidden forces or quantum principles we have yet to uncover. It might also shed light on the nature of gravity itself, helping us bridge the gap between the microscopic world of particles and the cosmic scale of black holes. As we continue to explore this paradox, experiments and observations are providing new clues. From gravitational wave detectors to advanced simulations, scientists are piecing together the puzzle of black holes and their mysterious behavior. Each discovery brings us closer to understanding whether information truly vanishes in a black hole or if it's preserved in ways we're only beginning to imagine. With this in mind, let's turn our attention to another fascinating theory: the nature of time and how it might function as a hidden force or dimension shaping the universe. Now let's step into the enigmatic realm of time itself, a dimension so familiar yet so mysterious. Time is more than just the ticking of a clock or the passing of days. It's a fundamental force woven into the fabric of the universe. But what if time isn't just a passive backdrop? What if it's an active, hidden force shaping the cosmos in ways we're only beginning to understand? One of the most intriguing ideas is that time might function as a dimension much like space. In Einstein's theory of relativity, time and space are intertwined into a single entity called spacetime. This means that time isn't just a linear progression. It can bend, stretch, and even warp under the influence of gravity. For instance, near a black hole, time slows down dramatically, a phenomenon known as time dilation. This suggests that time isn't just a constant flow but a dynamic force influenced by the universe's hidden mechanisms. But could time itself be a hidden force, Some theories propose that time might interact with other fundamental forces, like gravity or electromagnetism, in ways we haven't yet detected. For example, in certain quantum gravity models, time could emerge from the interactions of particles at the smallest scales. This would mean that time isn't just a dimension we move through, it's something that arises from the underlying structure of reality. Another fascinating concept is the idea of time as an emergent property. In this view, time isn't fundamental but rather a byproduct of more basic processes, like the entanglement of quantum particles. This challenges our traditional understanding of time as a continuous flow and suggests that it might be more like a series of discrete moments stitched together by hidden forces. Time also plays a crucial role in the universe's structure. Without time, there would be no change, no evolution, and no history. It's the dimension that allows galaxies to form, stars to burn, and life to emerge. Yet time's arrow, the direction in which time flows, remains one of the greatest mysteries. Why does time move forward and not backward? Some theories suggest that the expansion of the universe, driven by dark energy, might be linked to the direction of time. Others propose that time's arrow is tied to the increase of entropy, a measure of disorder in the universe. The nature of time also raises profound questions about causality and free will. If time is a dimension, does that mean the past, present, and future all exist simultaneously? Could hidden forces allow for time travel or even the manipulation of time itself? While these ideas remain speculative, they highlight the deep connections between time and the universe's hidden forces. As we continue to explore the mysteries of time, experiments in quantum mechanics and cosmology are shedding new light on its true nature. From atomic clocks that measure time with incredible precision to observations of distant galaxies that reveal the universe's history, each discovery brings us closer to understanding time's role in the cosmos. With this in mind, let's turn our attention to another captivating theory: the role of consciousness and how it might interact with the universe's hidden forces. Now, shifting our focus to the mind itself, let's explore the intriguing idea that consciousness might play a role in shaping or interacting with the universe's hidden forces. This theory sits at the crossroads of physics and philosophy, blending scientific inquiry with profound questions about the nature of existence. Could our awareness of the universe actually influence its behavior? It's a question that challenges both our understanding of reality and the limits of human perception. One of the most thought-provoking ideas in this realm is the notion that consciousness might be a fundamental aspect of the universe, much like space, time, or energy. Some theories propose that consciousness isn't just a byproduct of the brain, but a fundamental force that interacts with the fabric of reality. This perspective suggests that the act of observation, whether by a human or a machine, could influence the behavior of particles at the quantum level. This idea is rooted in the famous double-slit experiment, where particles behave differently when observed, hinting that consciousness might play a role in collapsing quantum possibilities into definite outcomes. Another fascinating angle is the concept of panpsychism, which posits that consciousness is a universal property of all matter. In this view, even the smallest particles possess a form of awareness, and the complex consciousness we experience emerges from the collective interactions of these particles. If true, this would mean that hidden forces might not just shape the universe, they might also be shaped by the consciousness inherent within it. This idea bridges the gap between physics and philosophy, raising questions about the nature of existence and the relationship between mind and matter. The intersection of consciousness and hidden forces also leads us to explore the role of intention and thought. Some theories suggest that focused human intention could influence physical systems, a concept explored in fields like parapsychology and quantum consciousness. While these ideas remain controversial and lack widespread scientific consensus, they open the door to fascinating possibilities. Could our thoughts and intentions interact with hidden forces in ways we don't yet understand? Could consciousness be a key to unlocking the universe's deepest secrets? At the same time, this theory raises profound philosophical questions. If consciousness is a fundamental force, what does that mean for free will, identity, and the nature of reality itself? Are we passive observers of the universe, or do we play an active role in shaping it? These questions challenge us to rethink our place in the cosmos and the nature of our connection to the hidden forces that govern it. As we continue to explore the mysteries of consciousness, experiments in quantum mechanics and neuroscience are shedding new light on its potential role in the universe. From studies on the brain's neural networks to investigations into quantum coherence in biological systems, each discovery brings us closer to understanding whether consciousness is a mere observer or an active participant in the cosmic dance. With this in mind, let's turn our attention to another captivating theory, the Ekpyrotic universe, which proposes a dramatic origin story for our cosmos involving higher dimensional collisions. Now, let's venture into a theory that paints a strikingly different picture of the universe's origins, the Ekpyrotic universe. This idea proposes that our cosmos wasn't born from a single explosive event like the Big Bang, but rather from a dramatic collision between higher dimensional structures known as brains. Imagine these brains as vast, multidimensional sheets floating in a higher dimensional space. When they collide, the energy released could have sparked the creation of the universe as we know it. This theory offers a fresh perspective on the universe's beginnings, one that challenges traditional narratives and opens up new possibilities for understanding hidden forces. In the Ekpyrotic model, hidden forces might play a crucial role in shaping the aftermath of these brain collisions. For instance, the energy and dynamics of the collision could have set the stage for the formation of matter, space, and even the fundamental forces we observe today. This theory suggests that hidden forces might not just influence the universe's current state, they could have been instrumental in its very creation. The idea of higher dimensional brains interacting in ways we can't directly observe adds another layer of mystery to the forces that govern our reality. One of the most intriguing aspects of this theory is how it connects to the concept of extra dimensions. In the Ekpyrotic universe, the brains exist in a space with more than the 3 dimensions we experience. These extra dimensions could be where hidden forces operate, influencing our universe from beyond our perception. This raises fascinating questions. Could hidden forces be the result of interactions in these higher dimensions? And if so, how might they manifest in our observable universe? The Ekpyrotic model invites us to consider that the forces we're trying to understand might be just the tip of a much larger, multidimensional iceberg. The Ekpyrotic universe theory also offers a potential solution to some of the puzzles in cosmology, such as the uniformity of the cosmic microwave background radiation. The collision of brains could have smoothed out irregularities, creating the remarkably even distribution of energy we observe. This suggests that hidden forces might have played a role in fine-tuning the universe's structure, ensuring the conditions necessary for galaxies, stars, and ultimately life to emerge. As we explore this theory, it's worth noting that the Ekpyrotic model isn't without its challenges. Detecting evidence of higher dimensional brains or the remnants of their collisions remains a significant hurdle. However, the idea itself pushes the boundaries of our understanding, encouraging us to think beyond the confines of traditional physics. It reminds us that the universe's hidden forces might be far more complex and interconnected than we've ever imagined. With this in mind, let's turn our attention to another fascinating concept: the role of magnetic monopoles, hypothetical particles that could hold the key to unlocking even more secrets about the universe's hidden forces. Now, shifting our focus to another intriguing piece of the cosmic puzzle, let's delve into the hypothetical world of magnetic monopoles. Unlike the familiar magnets we encounter in everyday life, which always have both a north and a south pole, magnetic monopoles are theorized to be particles with just a single magnetic charge, either north or south. This idea, while seemingly simple, could revolutionize our understanding of hidden forces and the fundamental laws of physics. The concept of magnetic monopoles arises from the equations of electromagnetism, which suggest that such particles could exist, even though none have been observed so far. If they do exist, magnetic monopoles would provide a missing symmetry in the laws of physics, completing the picture in a way that aligns with other fundamental forces. This symmetry could help unify our understanding of electromagnetism with other forces, potentially offering clues about the universe's hidden mechanisms. One of the most exciting implications of magnetic monopoles lies in their connection to grand unified theories, which aim to merge the electromagnetic, weak, and strong nuclear forces into a single framework. These theories predict that monopoles could have formed in the early universe during a phase of extreme energy and temperature. If true, these particles might still exist today, hidden in the vastness of space, waiting to be discovered. Their detection could provide direct evidence for grand unified theories and shed light on the forces that shaped the cosmos in its infancy. Magnetic monopoles also have fascinating implications for cosmology. Some theories suggest that these particles could have played a role in the formation of cosmic structures, such as galaxies and galaxy clusters. Their unique properties might have influenced the distribution of matter and energy in the early universe, leaving subtle traces that we could detect with advanced instruments. This makes the search for monopoles not just a quest for new particles, but also a journey into the origins of the universe itself. Despite their theoretical appeal, magnetic monopoles remain elusive. Experiments to detect them have so far come up empty, but scientists continue to refine their methods and explore new possibilities. From particle accelerators to cosmic ray detectors, the hunt for monopoles is a testament to humanity's curiosity and determination to uncover the universe's deepest secrets. As we ponder the existence of magnetic monopoles, we're reminded of how much there is still to discover about the forces that govern our reality. These hypothetical particles could be the key to unlocking new realms of physics, offering insights into the hidden forces that shape the cosmos. With this in mind, let's turn our attention to another compelling idea, the anthropic principle, which explores how the universe's constants might be fine-tuned for life. Now, let's explore a fascinating idea that shifts our perspective from particles to the very fabric of existence itself, the anthropic principle. This principle suggests that the universe's fundamental constants, like the strength of gravity, the speed of light, and the charge of an electron, are precisely fine-tuned to allow life to exist. If any of these constants were even slightly different, the universe as we know it might not have formed, and life as we understand it would be impossible. At its core, the anthropic principle raises a profound question. Why does the universe seem so perfectly suited for life? Some scientists argue that this fine-tuning isn't a coincidence but rather a reflection of deeper, hidden forces at work. These forces could be shaping the universe in ways we're only beginning to understand, ensuring that the conditions necessary for life are met. In this view, the constants we observe aren't random. They're the result of underlying mechanisms that guide the universe's evolution. One way to think about this is through the lens of multiverse theory. If our universe is just one of countless others, each with its own set of physical constants, it's possible that only a small fraction of these universes have the right conditions for life. In this scenario, hidden forces might determine which universes thrive and which ones fade away, effectively selecting for the ones where life can emerge. This idea ties the anthropic principle to the broader mystery of why our universe exists in its current form. Another angle involves the role of hidden forces in stabilizing the universe's structure. For example, dark energy, which drives the accelerated expansion of the cosmos, plays a crucial role in shaping the large-scale structure of the universe. If dark energy were stronger or weaker, galaxies might not have formed, and life as we know it wouldn't have had a chance to develop. Similarly, the balance between gravity and other fundamental forces ensures that stars can form and burn for billions of years, providing the energy needed for life to flourish. The anthropic principle also invites us to consider the possibility that life itself might influence the universe's hidden forces. Some speculative theories suggest that consciousness or observation could play a role in shaping reality, though this remains a highly debated and controversial idea. Whether or not this is true, the principle highlights the intricate interplay between the universe's physical laws and the emergence of life. As we reflect on the anthropic principle, we're left with a profound sense of wonder. The universe's fine-tuning suggests that there's more to reality than meets the eye, hidden forces that shape the cosmos in ways we're only beginning to uncover. And with that, let's turn our attention to another intriguing piece of the cosmic puzzle: the role of axions, hypothetical particles that could hold the key to understanding dark matter and the universe's hidden forces. Now, shifting our focus to a particle that might hold the key to one of the universe's greatest mysteries, let's explore the role of axions. These hypothetical particles, first proposed in the late 1970s, are thought to be incredibly lightweight and nearly invisible, making them a prime candidate for explaining dark matter. Unlike other particles, axions interact so weakly with ordinary matter that they've eluded detection so far, but their existence could solve some of the most puzzling questions about the cosmos. Axions were initially theorized to resolve a problem in particle physics known as the strong charge parity problem, which deals with the behavior of quarks and gluons in the strong nuclear force. But over time, scientists realized that axions could also play a crucial role in explaining dark matter. If axions exist, they could make up a significant portion of the universe's unseen mass, influencing the way galaxies rotate and cluster together. Their unique properties, being both extremely light and abundant, make them an ideal fit for the dark matter puzzle. One of the most exciting aspects of axions is how they might interact with hidden forces. If axions are real, they could be influenced by subtle, yet to be discovered forces that shape the universe on a fundamental level. For instance, some theories suggest that axions could interact with electromagnetic fields in ways that are currently beyond our detection capabilities. This interaction could create faint signals that, if detected, would not only confirm the existence of axions but also shed light on the hidden forces that govern the cosmos. To find these elusive particles, scientists have designed a variety of innovative experiments. One approach involves using powerful magnetic fields to convert axions into detectable photons. Experiments like the Axion Dark Matter Experiment, or ADMX, use superconducting magnets and ultra-sensitive detectors to search for these faint signals. Another method involves looking for axions produced in the sun, where high-energy processes might generate them in abundance. These solar axions could then be detected using specialized instruments designed to capture their unique signatures. While no definitive evidence of axions has been found yet, the search continues with increasing precision and creativity. Each experiment brings us closer to uncovering whether these particles exist and how they might fit into the larger picture of the universe's hidden forces. If axions are discovered, they could revolutionize our understanding of dark matter, particle physics, and the fundamental nature of reality itself. As we ponder the potential of axions, we're reminded of how much remains to be discovered about the cosmos. These tiny, elusive particles could be the missing piece in our quest to understand the universe's deepest secrets. And with that, let's turn our attention to another intriguing concept: the role of tachyons, hypothetical particles that might challenge our understanding of time and causality. Now, let's venture into the realm of the extraordinary, where the rules of physics as we know them might bend or even break. Enter tachyons, hypothetical particles that, if they exist, could travel faster than the speed of light. This idea alone challenges one of the most fundamental principles of modern physics: Einstein's theory of relativity, which states that nothing with mass can exceed the speed of light. But tachyons, by their very definition, defy this rule, opening up a world of possibilities and paradoxes. Tachyons are theorized to possess a peculiar property. As they gain energy, they slow down, and as they lose energy, they speed up. This is the opposite of how ordinary particles behave. For example, if you could somehow observe a tachyon, it might appear to move backward in time, creating mind-bending implications for causality, the relationship between cause and effect. If tachyons exist, they could potentially send information or influence events in ways that disrupt our understanding of time itself. Imagine a particle that could, in theory, arrive at a destination before it even left its starting point. This raises profound questions about the nature of reality and whether the universe allows for such phenomena. But how might tachyons interact with hidden forces? Some theories suggest that these particles could be influenced by or even mediate forces we have yet to discover. For instance, if tachyons exist, they might interact with the fabric of spacetime in ways that reveal new dimensions or hidden layers of the universe. Their faster-than-light nature could also mean they're connected to forces that operate outside the constraints of our current physical laws. This could provide a bridge between the known and the unknown, offering clues about how hidden forces shape the cosmos. The implications of tachyons extend beyond just physics. If these particles are real, they could revolutionize our understanding of communication, energy, and even time travel. Imagine a future where tachyons are harnessed to send messages instantaneously across vast distances, bypassing the limitations of light speed. Or consider the possibility that tachyons could unlock new forms of energy, tapping into the hidden forces that govern the universe. While these ideas remain speculative, they highlight the tantalizing potential of these elusive particles. Of course, the existence of tachyons is still purely theoretical. No experiment has yet provided evidence for their existence, and many physicists remain skeptical. However, the search for tachyons continues, driven by the allure of what they could reveal about the universe. Experiments involving particle accelerators and cosmic ray observations aim to detect any anomalies that might hint at their presence. Even if tachyons don't exist, the pursuit of understanding them pushes the boundaries of science, challenging us to think beyond the limits of our current knowledge. As we contemplate the mysteries of tachyons, we're reminded that the universe is far stranger and more complex than we can imagine. These hypothetical particles, with their potential to rewrite the rules of physics, invite us to explore the edges of what's possible. And with that, let's turn our attention to another fascinating concept: the role of wormholes, theoretical passages through space-time that could connect distant parts of the universe, or even different universes altogether. Now, let's shift our gaze to another mind-bending concept that has captured the imagination of scientists and science fiction enthusiasts alike: wormholes. These theoretical passages through space-time are often depicted as cosmic shortcuts connecting distant parts of the universe, or even entirely different universes. But what exactly are wormholes, and how might hidden forces play a role in their existence or stability? At their core, wormholes are solutions to the equations of general relativity proposed by Albert Einstein and Nathan Rosen in the 1930s. Often referred to as Einstein-Rosen bridges, these structures are essentially tunnels that link two separate points in spacetime. Imagine folding a piece of paper so that two distant dots touch. A wormhole would be the bridge connecting those dots, allowing for instantaneous travel between them. While this sounds like the stuff of science fiction, the math suggests that such structures could exist, at least in theory. However, there's a catch. Wormholes, as predicted by current physics, would be incredibly unstable. Without some form of stabilization, they would collapse almost instantly, making them useless for any practical purpose. This is where hidden forces come into play. Some theories propose that exotic forms of matter or energy, substances with negative energy density or unusual properties, could act as a stabilizing force, keeping a wormhole open long enough for something to pass through. These exotic materials would counteract the natural tendency of the wormhole to collapse under its own gravitational pull, effectively acting as cosmic glue. But what could these hidden forces be? One possibility is that they are connected to the quantum vacuum, the sea of virtual particles that constantly pop in and out of existence. The quantum vacuum is thought to contain immense amounts of energy, and some researchers speculate that manipulating this energy could provide the necessary conditions to stabilize a wormhole. Another intriguing idea is that dark energy, the mysterious force driving the accelerated expansion of the universe, might play a role. If dark energy can influence the large-scale structure of the cosmos, perhaps it could also be harnessed to create or maintain these space-time tunnels. The implications of wormholes are as vast as the universe itself. If they could be stabilized, they might offer a way to traverse unimaginable distances in the blink of an eye, revolutionizing space travel and our understanding of the cosmos. They could also provide a window into other dimensions or parallel universes, offering insights into the multiverse theory. And let's not forget the tantalizing possibility of time travel. Some wormhole models suggest that they could create closed time-like curves, allowing for journeys into the past or future. Of course, wormholes remain purely theoretical for now. No observational evidence has been found to confirm their existence, and the technological challenges of creating or stabilizing one are beyond our current capabilities. Yet, the study of wormholes continues to push the boundaries of physics, inspiring new ideas and experiments. They remind us that the universe is full of mysteries waiting to be uncovered, and that hidden forces, whether they stabilize wormholes or not, are key to unlocking those secrets. As we ponder the possibilities of wormholes, we're drawn to the next intriguing question. What role does quantum gravity play in the grand tapestry of the universe? This brings us to our next theory, where we'll explore how the quest to unify quantum mechanics and general relativity might reveal even more about the hidden forces shaping our reality. Now, let's venture into the fascinating realm of quantum gravity, a field that seeks to bridge two of the most profound yet seemingly incompatible theories in physics: general relativity and quantum mechanics. While general relativity beautifully explains the large-scale structure of the universe, think black holes, galaxies, and the curvature of space-time, quantum mechanics governs the behavior of the smallest particles like electrons and quarks. But when these two worlds collide, the result is a puzzle that has baffled scientists for decades. This is where quantum gravity steps in, offering a potential framework to unify these theories and, in the process, revealing how hidden forces might shape the cosmos. At its heart, quantum gravity is the quest to understand how gravity operates at the quantum level. In the world of the very small, particles don't behave like the objects we see in everyday life. Instead, they exist in a state of probability governed by the strange rules of quantum mechanics. But gravity, as described by Einstein's general relativity, is a smooth, continuous force that warps spacetime. The challenge lies in reconciling these two descriptions. How can gravity, which shapes the universe on a grand scale, also fit into the probabilistic, particle-like nature of the quantum world? One of the leading candidates for a theory of quantum gravity is string theory. This framework suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings oscillate at different frequencies, giving rise to the various particles and forces we observe. In this model, gravity emerges as one of the vibrations of these strings, offering a way to unify it with the other fundamental forces. But string theory also introduces the idea of extra dimensions, beyond the three spatial dimensions we experience where hidden forces might operate. These extra dimensions could be the key to understanding phenomena like dark energy or the stabilization of wormholes, as we discussed earlier. Another promising approach is loop quantum gravity, which reimagines spacetime itself as a network of interconnected loops. In this view, spacetime isn't smooth and continuous but made up of discrete, quantized units. This granularity at the smallest scales could prevent the singularities predicted by general relativity, such as those at the center of black holes. Loop quantum gravity also suggests that hidden forces might arise from the interactions of these spacetime loops, potentially explaining why gravity behaves differently at quantum scales compared to the macroscopic world. But what does all this mean for hidden forces? If quantum gravity successfully unifies general relativity and quantum mechanics, it could reveal new forces or interactions that we've yet to detect. For instance, some theories propose that quantum gravity might give rise to a force that operates only at extremely small scales, influencing the behavior of particles in ways we can't yet observe. Others suggest that hidden forces might emerge from the interplay between quantum fluctuations and spacetime itself, offering a deeper understanding of phenomena like dark matter or the quantum vacuum. The implications of quantum gravity are profound. Not only could it solve one of the biggest mysteries in physics, but it might also open the door to entirely new realms of discovery. By uncovering how gravity works at the quantum level, we could gain insights into the early universe, the nature of black holes, and even the possibility of parallel universes. And as we've seen throughout this exploration, hidden forces are often the key to unlocking these cosmic secrets. As we continue our journey through the mysteries of the universe, we turn our attention to another intriguing concept, supersymmetry. This theory proposes a hidden symmetry in nature that could explain some of the deepest questions in physics, including the nature of dark matter and the unification of forces. What role might supersymmetry play in the grand tapestry of the cosmos? Let's find out. Now, let's shift our focus to a theory that could fundamentally reshape our understanding of the universe, supersymmetry. This elegant idea proposes that every particle we know has a hidden partner, a kind of cosmic twin that we've yet to detect. Imagine a mirror world where every electron, quark, and photon has a corresponding superpartner with unique properties. This symmetry isn't just a fascinating concept, it could hold the key to solving some of the biggest mysteries in physics, including the nature of dark matter and the unification of forces. At its core, supersymmetry suggests that the universe operates with a hidden balance, a symmetry between particles that carry different types of spin. For instance, the familiar particles we interact with every day, like electrons and quarks, belong to a category called fermions. According to supersymmetry, each of these fermions has a superpartner known as a boson and vice versa. These superpartners, often referred to as sparticles, could exist at much higher energy levels, making them incredibly difficult to detect with current technology. But if they do exist, they could explain why the universe behaves the way it does. One of the most compelling reasons scientists are drawn to supersymmetry is its potential to solve the mystery of dark matter. As we've discussed earlier, dark matter makes up a significant portion of the universe's mass, yet it doesn't interact with light or ordinary matter in any way we can observe. Supersymmetry offers a tantalizing possibility. The lightest superpartner could be stable and invisible, making it a perfect candidate for dark matter. This particle, often called the Neutrino, could be floating through space right now, shaping galaxies and cosmic structures without us even realizing it. But supersymmetry doesn't stop there. It also provides a framework for unifying the fundamental forces of nature. In the standard model of physics, the four forces gravity, electromagnetism, and the strong and weak nuclear forces are described by different theories. Supersymmetry suggests that at extremely high energies, these forces could merge into a single, unified force. This unification would not only simplify our understanding of the universe, but also reveal how hidden forces might operate in a supersymmetric world. For example, the interactions between superpartners could give rise to new forces or modify existing ones in ways we've yet to imagine. Another intriguing aspect of supersymmetry is its connection to the Higgs boson, the particle responsible for giving other particles mass. In the Standard Model, the mass of the Higgs boson is surprisingly light, which has puzzled scientists for years. Supersymmetry offers an elegant solution. The superpartners of the Higgs boson could cancel out certain quantum effects, stabilizing its mass and explaining why it's so much lighter than expected. This interplay between particles and their superpartners could be a clue to how hidden forces maintain the delicate balance of the universe. Of course, supersymmetry isn't without its challenges. Despite decades of searching, no direct evidence of superpartners has been found. Experiments at the Large Hadron Collider and other particle accelerators have yet to detect these elusive particles, leading some to question whether supersymmetry exists at all. However, many scientists remain optimistic, believing that superpartners might simply be heavier than we've been able to probe so far. Future experiments with even higher energy levels could finally uncover these hidden partners and confirm the theory. If supersymmetry is proven true, it would revolutionize our understanding of the cosmos. Not only would it explain dark matter and unify the fundamental forces, but it could also reveal entirely new dimensions of reality. Hidden forces operating through the interactions of superpartners might govern phenomena we've yet to discover, from the behavior of black holes to the structure of spacetime itself. Supersymmetry reminds us that the universe is far more intricate and interconnected than we often realize. As we continue to explore the mysteries of the cosmos, our next stop takes us to the idea of extra dimensions. Could there be more to space than the three dimensions we experience? And if so, how might these hidden dimensions influence the forces that shape our universe? Let's dive in and find out. Now, let's venture into a realm that stretches the boundaries of our imagination, the possibility of extra dimensions. While we're accustomed to living in a world defined by three spatial dimensions, length, width, and height, some theories suggest there could be more to space than meets the eye. These extra dimensions, hidden from our everyday perception, might hold the key to understanding some of the universe's most profound mysteries, including the nature of hidden forces. The idea of extra dimensions isn't just science fiction. It's a serious proposal in modern physics. One of the most well-known frameworks that incorporates extra dimensions is string theory. According to this theory, the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. For the math to work, these strings need to vibrate in more than just the three dimensions we're familiar with. In fact, string theory suggests there could be as many as 10 or even 11 dimensions, all curled up and hidden at scales so small we can't detect them directly. But how could these extra dimensions influence hidden forces? One possibility is that forces like gravity, which we experience as relatively weak compared to other fundamental forces, might actually be much stronger in higher dimensions. In our three-dimensional world, gravity's strength diminishes with distance, but in extra dimensions it could behave differently. This could explain why gravity seems so feeble in our observable universe. It might be leaking into these hidden dimensions, spreading its influence in ways we can't fully perceive. Another intriguing idea is that particles and forces we're familiar with might be confined to our three-dimensional brain, a term borrowed from string theory that refers to a slice of higher dimensional space. Meanwhile, other particles or forces could exist in the full expanse of these extra dimensions, interacting with our world in subtle, almost imperceptible ways. For example, dark matter, which we've discussed earlier, might be a particle that exists primarily in these higher dimensions, only occasionally brushing up against our own. Extra dimensions could also provide a new perspective on the unification of forces. In our three-dimensional world, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces appear distinct. But in higher dimensions, these forces might merge into a single, unified force, revealing a deeper symmetry in the fabric of reality. This unification could explain how hidden forces operate across different scales, from the subatomic to the cosmic. Of course, the challenge lies in detecting these extra dimensions. Since they're thought to be incredibly small or tightly curled, they're beyond the reach of our current technology. However, some experiments, like those conducted at the Large Hadron Collider, are searching for indirect evidence. For instance, if particles collide with enough energy, they might create ripples or particles that briefly escape into these extra dimensions, leaving behind telltale signs in our observable universe. The concept of extra dimensions opens up a world of possibilities, from explaining the weakness of gravity to shedding light on dark matter and the unification of forces. It reminds us that the universe might be far more complex and interconnected than we've ever imagined. As we continue to explore these ideas, we're not just uncovering hidden dimensions, we're redefining our understanding of reality itself. With this in mind, let's turn our attention to another fascinating concept: cosmic strings. These hypothetical one-dimensional defects in space-time could hold clues to the universe's earliest moments and the forces that shaped it. What are they, and how might they influence the cosmos? Let's unravel this mystery next. Now, shifting our focus to another intriguing concept, let's explore the idea of cosmic strings. These hypothetical one-dimensional defects in space-time are thought to be remnants from the earliest moments of the universe, formed during a phase transition as the cosmos cooled and expanded. Imagine space-time as a fabric and cosmic strings as tiny, incredibly dense threads woven into it, stretching across unimaginable distances. While they've never been directly observed, their existence could help explain some of the universe's most puzzling features, including the role of hidden forces. Cosmic strings are theorized to be incredibly thin but extraordinarily massive, with a thickness smaller than an atom but a mass comparable to a mountain. Despite their minuscule size, their gravitational influence could be profound. As they move through space-time, they might create ripples in the fabric of the universe, generating gravitational waves that could be detected by advanced observatories. These waves could carry information about the early universe, offering clues about how hidden forces operated during its infancy. One of the most fascinating aspects of cosmic strings is their potential to influence the large-scale structure of the universe. As they drift through space, they could act as gravitational lenses, bending light from distant galaxies and creating unique patterns that astronomers might observe. These distortions could reveal the presence of cosmic strings, even if they remain invisible to direct detection. Additionally, cosmic strings might play a role in seeding the formation of galaxies and galaxy clusters, acting as cosmic scaffolding that guided the growth of matter in the early universe. But how do cosmic strings connect to hidden forces? One possibility is that they are relics of a time when the fundamental forces of nature were unified. During the universe's earliest moments, these forces, gravity, electromagnetism, and the strong and weak nuclear forces, might have been indistinguishable. As the universe expanded and cooled, these forces separated, and cosmic strings could have formed as a byproduct of this process. In this way, they might carry imprints of the unified force, offering insights into how hidden forces operated before the universe as we know it took shape. Another intriguing idea is that cosmic strings could interact with dark matter or dark energy, the mysterious components that make up most of the universe. For instance, cosmic strings might act as conduits for dark matter, channeling its influence across vast distances. Alternatively, they could be linked to dark energy, contributing to the accelerated expansion of the universe in ways we don't yet understand. These connections could help bridge the gap between the visible and invisible aspects of the cosmos, shedding light on the forces that govern its behavior. While cosmic strings remain theoretical, their potential impact on our understanding of the universe is immense. They could provide a window into the earliest moments of creation, reveal the nature of hidden forces, and even reshape our understanding of space-time itself. As scientists continue to search for evidence of these elusive structures, we're reminded that the universe is full of mysteries waiting to be uncovered. With this in mind, let's turn our attention to another captivating theory, the Inflaton field. This hypothetical field is thought to have driven the rapid expansion of the universe during its earliest moments. How does it connect to hidden forces, and what does it tell us about the birth of the cosmos? Let's dive into this next chapter of our exploration. Now, let's journey back to the very beginning of the universe, where one of the most pivotal events in cosmic history took place: cosmic inflation. At the heart of this rapid expansion lies a mysterious entity known as the Inflaton field. This hypothetical field is believed to have played a crucial role in shaping the early universe, driving its exponential growth in a fraction of a second after the Big Bang. But what exactly is the Inflaton field, and how does it connect to the hidden forces that govern our cosmos? The Inflaton field is thought to be a quantum field that permeated the early universe, acting as a kind of cosmic engine. As the universe expanded, this field underwent a phase transition, releasing an enormous amount of energy that fueled inflation. This process smoothed out the universe, creating the remarkably uniform conditions we observe today in the cosmic microwave background radiation. Without the Inflaton field, the universe might have remained a chaotic, uneven mess, making the formation of galaxies, stars, and planets nearly impossible. One of the most intriguing aspects of the Inflaton field is its connection to hidden forces. During inflation, the field's energy density dominated the universe, effectively masking the influence of other forces like gravity and electromagnetism. As inflation ended, the Inflaton field decayed, releasing its energy and allowing the fundamental forces we know today to emerge. This transition might hold clues about how hidden forces operated in the early universe, offering a glimpse into a time when the laws of physics were vastly different from what we experience now. The Inflaton field also raises fascinating questions about the nature of hidden forces. Could it have interacted with dark matter or dark energy, the mysterious components that make up most of the universe? Some theories suggest that the Inflaton field's decay might have produced particles that later became dark matter, or that its residual energy could have contributed to the dark energy driving the universe's accelerated expansion. These possibilities highlight the Inflaton field's potential role as a bridge between the visible and invisible aspects of the cosmos. Another compelling idea is that the Inflaton field might have left behind subtle imprints in the universe's structure. Tiny quantum fluctuations in the field during inflation could have been stretched to cosmic scales, seeding the formation of galaxies and galaxy clusters. These fluctuations might also carry information about the hidden forces that influenced the Inflaton field, providing a unique window into the universe's earliest moments. While the Inflaton field remains a theoretical concept, its implications are profound. It not only explains the rapid expansion of the early universe, but also offers a potential link to the hidden forces that shape our reality. As scientists continue to explore this idea, we're reminded that the universe's greatest mysteries often lie in its most fundamental processes. With this in mind, let's turn our attention to the final piece of the puzzle, the quantum vacuum. This enigmatic sea of virtual particles and energy might hold the key to understanding the hidden forces that shape the cosmos. What secrets does it reveal, and how does it tie everything together? Let's explore this next chapter in our journey through the universe's hidden forces. Now, as we venture into the final chapter of our exploration, we arrive at the quantum vacuum, a concept that might sound like empty space but is anything but. Imagine the quantum vacuum as a bubbling, energetic sea, teeming with virtual particles that pop in and out of existence in the blink of an eye. This isn't just a theoretical curiosity. It's a fundamental aspect of the universe that could hold the key to understanding the hidden forces shaping everything around us. At its core, the quantum vacuum is the lowest possible energy state in the universe, but don't let the term vacuum fool you. Far from being empty, it's a dynamic arena where particles and antiparticles spontaneously appear and annihilate each other. These fleeting particles, known as virtual particles, are a direct consequence of the uncertainty principle in quantum mechanics. They exist for such a short time that they're impossible to detect directly, yet their effects are undeniable. One of the most fascinating aspects of the quantum vacuum is its connection to hidden forces. The constant creation and destruction of virtual particles generate tiny fluctuations in energy, which can influence the behavior of larger systems. For instance, the Casimir effect, which we discussed earlier, is a direct result of these quantum fluctuations. But beyond this, the quantum vacuum might also be the source of more profound forces that shape the cosmos on a grand scale. Some scientists propose that the quantum vacuum could be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. The vacuum's inherent energy, often referred to as zero-point energy, might contribute to the repulsive force pushing galaxies apart. If true, this would mean that the quantum vacuum isn't just a passive backdrop but an active participant in the universe's evolution. Another intriguing possibility is that the quantum vacuum could interact with dark matter, the invisible substance that makes up a significant portion of the universe's mass. Virtual particles in the vacuum might occasionally interact with dark matter particles, influencing their distribution and behavior. This interaction could provide clues about the nature of dark matter and how it fits into the larger cosmic puzzle. The quantum vacuum also raises profound questions about the nature of reality itself. If the vacuum is filled with energy and virtual particles, could it be the foundation of all matter and forces? Some theories suggest that the particles we observe, like electrons and quarks, might be excitations of the quantum vacuum, much like ripples on the surface of a pond. This idea blurs the line between something and nothing, challenging our understanding of existence. As we wrap up our journey through the universe's hidden forces, the quantum vacuum stands as a testament to the complexity and wonder of the cosmos. It reminds us that even the emptiest spaces are brimming with potential, offering endless opportunities for discovery. From the Inflaton field to the quantum vacuum, each theory we've explored reveals a piece of the grand puzzle, inviting us to keep questioning, exploring, and marveling at the universe's mysteries. And with that, we conclude our exploration of 30 theories about the universe's hidden forces. But the journey doesn't end here. There's always more to uncover, more questions to ask, and more wonders to behold. What do you think lies beyond these theories? Share your thoughts in the comments below. And don't forget to like, subscribe, and hit the notification bell to join us on our next cosmic adventure. Until then, keep looking up. The universe is waiting. As we bring our journey through the universe's hidden forces to a close, it's remarkable to reflect on the sheer diversity of ideas we've explored. From the invisible grip of dark matter shaping galaxies to the enigmatic push of dark energy accelerating the cosmos, each theory offers a unique lens through which to understand the mysteries of existence. We've ventured into the strange world of quantum entanglement, where particles communicate instantaneously across vast distances, and pondered the possibility of extra dimensions hidden within the fabric of reality. We've even considered the mind-bending idea that our universe might be a simulation, with hidden forces acting as the code behind the scenes. Theories like string theory and the holographic principle challenge us to rethink the very nature of space, time, and matter, while concepts like the Inflaton field and the quantum vacuum remind us that even the emptiest spaces are teeming with potential. The quest for a theory of everything continues to drive scientists forward, as they search for a unified framework that can explain all the forces at play in the universe. And let's not forget the tantalizing hints of a fifth force, or the role of neutrinos and axions in shaping cosmic phenomena. Each idea, whether proven or speculative, adds a piece to the puzzle, bringing us closer to understanding the grand tapestry of the cosmos. What's truly inspiring is how these theories, though diverse, all point to the same truth. The universe is far more complex and wondrous than we can imagine. They remind us that curiosity and exploration are at the heart of science, driving us to ask questions and seek answers, no matter how elusive they may seem. So, as we wrap up this exploration, I leave you with this thought. What do you think lies beyond these theories? Could there be forces or dimensions we haven't even conceived of yet? The universe is full of mysteries waiting to be uncovered, and the journey of discovery is far from over. If you've enjoyed this deep dive into the universe's hidden forces, don't forget to share your thoughts in the comments below. Which theory fascinated you the most? Let's keep the conversation going. And if you're eager for more cosmic adventures, hit that like button, subscribe, and ring the notification bell so you never miss out on our next exploration. Until then, keep looking up. The universe is full of wonders, and the next big discovery could be just around the